Okay, hello everyone. Let us continue the third part of today's class. Okay, so let us see this matrix. Okay, so the last row of this matrix should be JIM, where I is equal to 1 to n. So this should be JIM. And the first element I is equal to 1. So change I to 1. And this should be horizontal dots. And the last element is capital JIM, and I is equal to n. So change I to n. Good. And for this vector, let us see, it should be delta yi, I is equal to 1 to n. So let us copy delta yi, and the first element I is equal to 1. So we change I to 1. And then the vertical dots. And the last element should be delta yi, where I is equal to n. So I should be changed to n. And observing this matrix, we find that J11 to Jn1 and J1m to Jnm. Actually, we have seen this matrix earlier. So this matrix is just this matrix. So this matrix is J transpose. J transpose. J transpose, and times this vector. Let us call this vector delta y. Delta y. So let us call this equality A. Not this. A should be above. And here should be the equality sign, and A should be non-italic. Good. So let us align at the equality sign. Align at the equality sign. So this is not an equality sign. So that is okay. Equality sign and align. And let me input above A and the equality sign. So it is the equality sign. So I cannot align these two symbols. So I need to use a more stupid method to align them. So let me this equation adjust as the center, and this equation align left. this is center. Okay, and this align left. Okay. Okay, and let me put a lot of spaces here. Okay, like this. Okay, so this is equation 7. So I still cannot align this and this. Okay, never mind. Okay, this should be a bug of the Microsoft Word. Okay, where small w equality A results from letting delta y is equal to this vector. And this is equation 8. Finally, substituting equation 6 and equation 7 into equation 1, we have, let us see equation 6. J transpose J delta beta, and the equation 7 is J transpose delta y, and substituting equations 6 and 7 into 1. So they are equal to each other. So equation 6 is equal to equation 7. Like this. So it is equation 9. So it completes the solution of this problem. Align right. Safe. Good. So let us go back to the handout. So we just derive this equation, that is equation 62. These are the defining equations of the Gauss-Newton algorithm. So because of the time limitation, I do not plan to introduce Gauss-Newton algorithm. So next, problem 47. Derive the second equality in equation 53 in the handout. Let us go to equation 53. So the second equality. It should be equation 54. Should be this equality. I will fix this mistake later. So we have derived this. Derives equation 60 done, and derive equation 62. Done. Problem 50. What is Gauss-Newton algorithm? Solution. Because of time limitation, I do not plan to introduce it here. Because time is not enough. So I cannot explain all the proper nouns to you. Problem 51. What is maximum likelihood estimation? It is very important. Especially you are students in Department of Communications Engineering. Solution. In statistics, maximum likelihood estimation, abbreviated MLE, is a method of estimating the parameters of an assumed probability distribution given some observed data. This is achieved by maximizing a likelihood function. Okay, we will see what is a likelihood function later. So that under the assumed statistical model, the observed data is most probable. The point in the parameter space that maximizes the likelihood function is called the maximum likelihood estimate. The logic of maximum likelihood is both intuitive and flexible, and as such the method has become a dominant means of statistical inference. Okay, if the likelihood function is differentiable, okay, I know you have learned what is a differentiable function in the course calculus. Okay, if you forget, please review the textbook of the course calculus. The derivative test for determining maxima can be applied. In some cases, the first order conditions of the likelihood function can be solved explicitly. For instance, the ordinary least squares estimator. Okay, we have introduced what is least squares, okay, in the previous pages. If you forget, please see the handout on the previous pages. Maximizes the likelihood of the linear regression model. Under most circumstances, however, numerical methods will be necessary to find the maxima of the likelihood function. Okay, from the perspective of Bayesian inference, MLE is generally equivalent to maxima a posteriori, that is abbreviated MAP estimation under a uniform prior distribution on the parameters. In frequentist inference, MLE is a special case of an extremum estimator with the objective function being the likelihood. Okay, so it is a brief introduction to maximum likelihood estimation. Okay, so next let us see the principles of the maximum likelihood estimation. Okay, we model a set of observations as a random sample from an unknown joint probability distribution, which is expressed in terms of a set of parameters. The goal of maximum likelihood estimation is to determine the parameters for which the observed data have the highest joint probability. We write the parameters governing the joint distribution as a vector theta. Okay, theta is equal to theta 1, theta 2 dots theta k transpose. Okay, so we can see that there are k parameters, so that this distribution falls within a parametric family. Okay, f of dot theta given theta is in capital theta. Okay, where capital theta is called the parameter space, a finite dimensional subset of Euclidean space. Okay, evaluating the joint density at the observed data sample, y is equal to y1, y2 to yn. Okay, so there are totally n data. Okay, gives a real valued function. Okay, let us see. Ln of theta is equal to ln of theta y, okay, which is equal to fn of y theta. Okay, which is called the likelihood function. For independent and identically distributed random variables, fn of y theta will be the product of univariate density functions. Okay, let us see. Okay, fn of y theta is equal to the product from k is equal to 1 to n. Okay, fk, okay, univar means univariate of yk theta. Okay, what does the word univariate mean? Okay, it means that a function only has one variable, okay, which is yk here. Okay, because y1 to yn are independent, so according to the definition of the independence, their joint probability density function can be written as the product of the marginal probability density functions. Okay, like this. Okay, the goal of maximum likelihood estimation is to find the values of the model parameters that maximize the likelihood function over the parameter space, that is. Okay, theta hat, okay, when we add a hat, okay, it is read hat, okay. When we write a hat above a letter or a symbol, okay, it denotes the estimation of the symbol, okay, theta, is equal to arg max. Okay, what is arg max? Okay, it is the abbreviation of argument maximize. Okay, so the maximum is taken over all theta or small theta, which is in capital theta, and L hat n of theta y. Okay, so you can see that what does this mean? This means that we need to find a theta such that L hat of n of theta y is maximized. Okay, so the optima theta is the output of the arg max operator. Okay, intuitively this selects the parameter values that make the observed data most probable. The specific value theta hat is equal to theta hat n of y. Okay, because the estimation of theta is related to y and is a function of y. Okay, and the theta hat, of course, is in capital theta, because theta is in capital theta. So the optima theta, that is theta hat, is also in the set capital theta. That maximizes the likelihood function Ln. Okay, is called the maximum likelihood estimate. Okay. Okay, further, if the function theta hat n, okay, Rn to capital theta. Okay, what does this notation mean? Okay, this notation means that there is a function. The name of the function is theta hat n. and the domain of the function is Rn, and the range of the function is capital theta. Okay, then what is Rn? Or more exactly, R to the power of n. Okay, it means the n-dimensional real vector space. Okay, and I think you already know that R is the set which contains all real numbers. Okay, further, if the function theta hat n from Rn to capital theta, so defined is measurable. Okay, we will explain what is a measurable function later. Then it is called the maximum likelihood estimator. It is generally a function defined over the sample space. Okay, excuse me. That is taking a given sample as its argument. Okay, so you can see that theta hat n of y. So y is a given sample as its argument. A sufficient but not necessary condition. Okay, do you know what is sufficient condition and necessary condition? Okay, I suppose you have learned it when you are senior high school students. Okay, because when I was a senior high school student, I learned what are sufficient condition and necessary condition in the course mathematics. Okay, if you do not know what are sufficient condition and necessary condition, please tell me, and I will explain it in later classes. Okay, for its existence is for the likelihood function to be continuous over a parameter. Space capital theta that is compact. Okay, what is a compact space? Okay, we have introduced what is a compact set before. Okay, let me show you. Okay, compact set. Okay, here compact set. Okay, problem 11. What is a compact set? Okay, however, compact space is another concept, and I will introduce it later. Okay, for an open capital theta. Okay, here open means that capital theta is an open set. Then what is an open set? Okay, we also have introduced what is an open set. Okay, before. Okay, let me show you. Okay, open set. Okay, here. Okay, it is in problem 8. So if you forget what is an open set, please review the solution to problem 8. Okay, let us go back to let me search open. Okay, many opens. Open. Oh, many opens. Okay, good. Here. Okay, for an open capital theta, the likelihood function may increase without ever reaching a supremum value. Okay, we have introduced what is. Okay, it is 25 minutes. See you next time. Goodbye.